Swayam Prabha. Digital India. Educated India.
So, students, we are once again meeting for a lecture on shear strength of soils. We have had 4 lectures so far. This is the 5th in the series, and in this lecture we are going to move forward and see some detailed mechanisms that are going to be involved in the tests about which we have already discussed. In the previous 4 lectures, we had primarily discussed what is Morse circle, how stresses are represented by Morse circles, and how Morse circles help us to identify the planes of failure and the stresses at failure, and to understand in general the failure mechanisms involved in soils. In this lecture, we shall be going a step further. Now, for example, in the last lecture, I had mentioned that we have divided this chapter on shear strength into 3 major aspects. One is what are the different types of equipment used and what are the kinds of tests that are done with that. Then we have a section called drained and undrained tests. That is, in the case of soils, drainage is a very important aspect. Therefore, the type of tests that are done on soils can be classified according to the drainage that is either provided or absent. Lastly, the nature of the soil is obviously important, and therefore, we also will see what is shear strength and how it depends upon the nature of the soil itself. Now, this is the way I had subdivided the topics, and then the type of equipment used and the classification of the tests according to the type of equipment used was also seen in the past few lectures. For example, we have seen the direct shear, triaxial shear and the unconfined compression tests in detail. Before proceeding further, let us slightly recapitulate what we saw in these 3 sections. Let us take a brief review of the direct shear test, the triaxial shear test and the unconfined compression test. First, the direct shear test. What is important here is to understand how the stresses vary in the different planes during a direct shear test, which is the failure plane, what is the value of the stress during failure on the plane of failure, and how does the failure plane lie in relation to the applied stresses or the major and minor principal stresses. For example, if you see this small rectangle, this is the sample. There is a horizontal plane of failure. A normal stress sigma is applied and a corresponding shear stress tau is applied until this fails. Obviously, since on this horizontal plane of failure there is a shear stress, this cannot be the principal plane. The principal planes will therefore be the plane shown yellow in this, which is experiencing a normal stress equal to the major principal stress sigma 1. Perpendicular to that, the magenta colored plane carries a stress sigma 3. Now, if we see the depiction of the stress state in the Morse circle, we find that this A represents the stress sigma 3, B represents the stress sigma 1, and the major principal plane and the minor principal plane will both be parallel to the planes of sigma 1 and sigma 3 meeting at a point OP. Now, this point OP, known as the origin of planes, is a point such that the line drawn parallel to a known plane where it meets the circle, that point has the coordinates which are equal to the stresses on that plane. Now, we know that the plane of failure is horizontal, and therefore, COP must give the origin of planes. Now, this correspond, if I draw a horizontal line here, therefore, point C must be the plane of failure, which can also be obtained from the tangent OC. Now, the point C has stresses equal to sigma and tau, which are the stresses on the failure plane. In the case of Morse circle for a triaxial shear test, we generally do at least three tests and plot 3 more circles and draw a common tangent from which we get the normal and the shear stresses, the shear strength parameters. Now, here is an example of 3 such Morse circles for a triaxial test. For convenience, the first circle is shown to have a minor principal stress equal to sigma 31 and a major principal stress equal to sigma 11. The second circle, corresponding to the second test, has a slightly higher minor principal stress sigma 32 and a slightly correspondingly higher major principal stress sigma 12. The last circle has sigma 33 and sigma 13 as the corresponding stresses. Now, if I draw a common tangent to all these, then the intercept made by the tangent is the cohesion, and the angle which the tangent makes with the horizontal is the angle of friction. This is how the Morse circle test data is plotted and the shear strength parameters are obtained. Now, it is easy to show that from the Morse circle a relationship like this can be derived. At failure, it is possible to show that this relationship holds. In fact, we have done this, or we have seen that this relationship holds in one of my earlier lectures. The advantage of representing the more stress state in this form is that we can plot a straight line between the quantities sigma 1 minus sigma 3 by 2, which represents the deviatory stress by 2, that is the shear stress, and sigma 1 plus sigma 3 by 2, that is the stress invariant divided by 2. If I plot this will also be a straight line because this relationship is essentially linear, and by doing so we now get an intercept and an angle. It is very simple to show that this intercept will be nothing but c cos phi, that is the constant in the linear equation, and the angle will be nothing but an angle phi double dash, tangent of which must be equal to the sin phi, which is the slope of this linear equation. Thus, the triaxial test data can be plotted either in the form shown earlier using 3 Morse circles, or in the form of a PQ plot. The PQ plot is generally preferred because it is always easier to plot a straight line than to draw a common tangent to 3 Morse circles. Now, we go on to the unconfined compressive strength test. This test, as you know, is a special case of a triaxial test. The difference between the triaxial test, conventional triaxial test as it is called, and this test is that the confining stress sigma 3 is 0. Hence, it is necessary that the sample should be able to stand in the apparatus without confinement. Such a soil which will yield a sample which can stand in the apparatus without a confining pressure is a cohesive soil, and therefore, this test is usually employed to test only cohesive soils. The specimen can be kept in place without confinement, and since it is cohesive and since there is no confinement, the axial load is usually applied rapidly until failure, so that the specimen does not get dislodged. Such a rapid test obviously provides undrained conditions, and therefore friction does not get mobilized, and phi undrained equal to 0 holds for this test. And from this test, by plotting a Morse circle, we can get the cohesion as shown in this diagram. Since there is no confining pressure, since sigma 3 is equal to 0, unlike a conventional triaxial test, this will only have one single Morse circle corresponding to sigma 3 equal to 0, which starts from the origin. The axial stress at failure automatically is equal to the compressive strength, and half of that becomes the cohesion intercept, as you can see from this diagram. So, the cohesion is Qu upon 2 as far as this test is concerned. What is the importance of this unconfined compression strength test? The importance lies in the fact that it gives a very good indication of the consistency of the soil. For example, it is found that as Qu varies from 0 to some value more than 380 or 400 kilopascals, the consistency of the soil varies from a very soft state to a very hard state. Therefore, this Qu is a very good measure of the consistency, and this table gives you an idea about what is very soft, what is soft, medium, stiff, or very stiff and hard. Now, let us take a simple example of an unconfined compression test. Obviously, we need to know the dimensions of the specimen, that is given here, 38 millimeter diameter and 76 millimeter length. During the test, the vertical deformation was measured and was found to be 10 mm, corresponding to a load of 0.25 kilonewtons at which the sample failed. Now, what is required is to compute Cu. It is of course obvious that the simplest way is to plot a Morse circle and get the value of Cu, or rather we can also do analytically, and it is very important to note this first step in the analytical calculation. The first step is what is the value of the area at failure of this specimen, because the starting area is given by 38 millimeter diameter. On the other hand, since the deformation takes place in the vertical direction as the load is applied, due to Poisson effect, the horizontal diameter increases, and there is a deformation taking place in the horizontal direction, which therefore makes the effective area slightly different. So, if we start with an original area given by pi d square by 4, then that divided by 1 minus the vertical strain gives you the new area, and compressive strength has to be calculated by dividing the applied load at failure by this new area, and that comes out to be 192.31 kilonewton per meter square, and half of that becomes the cohesion. Now, all this actually we had seen in the previous lectures. This was to help you to recapitulate so that there will be a continuity. Now, in today's lecture, we will continue and see the fourth test that is remaining in this list of equipment and corresponding tests, Vane shear test. Namely, let us see, in this lecture we will also be seeing the second aspect of my classification of the entire lectures on shear strength, that is the second aspect, that is classifying the shear strength studies into those corresponding to drained state and those corresponding to undrained state. Let us begin with Vane shear test. This Vane shear test makes use of an apparatus called a vane. This vane consists of a rod, a set of vanes, 2 vanes to be precise. This has got a width equal to d and a height equal to capital H. There is a steel rod and there is a handle to apply a torque. Now, this vane is pushed into the soil gently and rotated until the soil fails. This particular test is such that it can be either done in the field or in the lab. The equipment that is used in the field is slightly large in dimensions. Diameter is 50 to 100 millimeter, height is 100 to 200 millimeters, and it can go up to 8 meters depth in very soft soils. On the other hand, if we want to do this in a laboratory sample, the equipment has to be much smaller in dimension. D is usually around 12.5 mm and the height is double that, 25 mm. This test is again very similar to the unconfined compressive strength test in the sense that it is valid mainly only for plastic cohesive soils. It is usually conducted in the laboratory, but it is good for field as well. The vane is usually very gently pushed into the soil so that it does not disturb the soil, and then a torque is applied to the handle or the rotating rod which is at the top until slowly the vane rotates and shears the soil and the soil fails in shear. Rotation at a slow speed is very important. Usually the rotation is done at approximately 0.1 degree per second rate. The maximum torque applied is obviously the total shear resistance. Now we can make computations or derive expressions from which we can compute the total torque applied and the corresponding shear resistance. How do we do that? If we take the torque versus the rotation, usually the relationship is like shown in this figure. It takes a value which corresponds to the peak here, and then after the soil fails, the torque comes down. The torque goes on increasing until failure and then it comes down. The vane itself experiences stresses as it cuts through the soil. It experiences shear stress along the faces on the sides as well as at the top and the bottom. Usually the shear resistance distribution is taken as uniform on the two sides, and at the top it is taken as either uniform, and so is the case with the bottom. What is shown here is a more generalized distribution than a uniform one, that is a parabolic end shear distribution, whether it is top end or at the bottom end. The shear resistance offered by the soil is assumed to be having a parabolic distribution. Now, how do we arrive at an expression at the time of failure? The shear resistance along a cylindrical surface is pi dh tau f. Why do we consider a cylindrical surface? It is very easy to imagine. As the torque is applied and the vane rotates, it cuts a cylindrical surface through the soil, and therefore the shear resistance of the soil is mobilized along this cylindrical surface. If tau f is the unit shear resistance, then pi dh, which is the surface area, into tau f becomes the total shear resistance along the side cylindrical surface. Whereas the shear resistance along the top and the bottom surfaces together will be twice 0 to d by 2, because d by 2 is equal to the radius, and the shear distribution is from the center to the outer edge. 2 pi r into dr tau f gives you the total shear resistance over a small elemental length dr at the ends. Now, when this is integrated, we will get a final expression for capital T, the total torque, which is the sum of the shear resistance along the cylindrical surface and the shear resistance along the top and bottom surfaces, and one can easily do this integration and see that the final expression for torque is pi d square tau f capital H by 2 plus small d by 6. Here we have assumed, as I mentioned some time back, uniform shear at top and bottom ends, and this is quite valid as long as H by d is greater than 3. But if that is not So, if h by d is not greater than 3, then we may apply or we have to apply a small correction, and then this expression will be written in terms of a correction factor A and d by 4. The correction factor is 0.67, 0.6 depending upon whether we have a parabolic or triangular end shear distribution. Now, if it is uniform, this A d by 4 becomes d by 6 and A becomes 1/3 in fact. If the upper surface does not take part in offering shear resistance, that is if the vein is not pushed completely into the soil, then T, the torque will only be d by 12, because the contribution from the bottom surface only will be there, the contribution of the top surface will not be there. And in all these, tau f is the unknown, and that is what we determine from knowing the torque and this expression and all the geometry of the vein, and that is what is equal to the undrained cohesion of the soil. The shearing of the soil is done relatively rapidly, so that we get an undrained cohesion value in this test. Now, having seen the theory behind the vein shear test and the expression that is used for computing the torque in terms of a tau f value, let us see an example of how this is used. There is a typical torque, the value of which is around 50 Newton per meter for a typical soil. The dimensions of the vein are also known. This particular example which I want to discuss is that of a field vein shear test. Knowing the geometry of the vein and that a typical value of 50 Newton meter torque is obtained at failure, we will calculate Cu. So, the statement of the problem is a saturated marine clay deposit, that means this test is done in clay as I have been saying, required a torque of 50 Newton meter at failure. The dimensions of the vein were 50 and 100 mm. It is also given that the vein was completely inside the soil, which means both the top and bottom surfaces participated in offering shear resistance. Compute the value of Cu. Obviously, Cu can be obtained by dividing capital T by this expression which we had derived earlier, and this will give us a Cu value of 109.13 kilonewton per meter square. Now, that completes the vein shear test and its usefulness and its application. Now, in this particular lecture, we will go now forward and take the second subdivision, that is drained and undrained tests. Now, it is very well known, we have discussed it sufficiently often, frequently in both my lectures on consolidation as well as in this, that when a soil is saturated and when a load is applied, be it compressive or be it shear, whenever a load is applied, if the drainage is permitted, then the load gets applied to the transferred to the soil grains as intergranular stresses. Otherwise, they remain as neutral stresses in the soil in the form of excess pore pressures until the water drains off and the stresses are transmitted to the grains. In the case of shear tests as well, when the shear force is applied to the soil, in the test for example, when the shear force is applied, depending upon whether there is drainage or not, the applied stress will get transmitted first to the water and then to the soil grains. And therefore, it is very important to know what is the condition with respect to drainage in a typical shear strength test. Let us see the next slide, drained and undrained tests. In my earlier lectures, I have told that development of effective stresses is associated with volume change and by pore water pressure change. Therefore, if we apply a shear force and do not allow volume change, then pore pressures will be developed. And the equation, well known equation, that total pressure is equal to effective pressure plus pore water pressure will be valid. Thus, drainage plays a very important role. And what is this drainage? Why is it important? It is important because actually it is a relative term. When I say there is drainage provision during a test, what it means is that the rate of shearing is such that water has enough time to flow out of the soil. On the other hand, if I say that the test is conducted under undrained conditions, it could mean either that there is no passage for the water to go out, or it could mean that the shearing is done so rapidly that water does not get time to get a free passage out. Now this is important because whereas in a laboratory test we can create conditions of complete drainage or complete no drainage, in the field it is not possible. In the field there could be either completely drained conditions. For example, if the soil is a granular soil, sand, then soil is highly pervious and complete drainage conditions could exist. On the other hand, if the soil is clayey, complete drainage conditions will never exist. There will always be partial drainage, and depending upon the rate of shear, water will either be allowed to flow out or not, and therefore the rate of shear relative to the rate of flow of water decides whether or not the condition is drained or undrained. So it is a relative term. Now if you see this next slide, it shows very clearly that if we use total stresses, then we will have shear strength given by the expression C plus sigma tan phi. If we measure the pore pressures and if we calculate the effective stress sigma dash, then the shear strength can be expressed in terms of the effective strength parameters C dash and phi dash, and the stress sigma dash, which is the effective stress, will depend upon the total stress applied and the measured pore pressure U. So depending upon the drainage, either we will have total stress or effective stress. Accordingly, as you will be seeing later, in some tests we will only be getting total stress shear strength parameters, and in some tests we will be getting effective stress shear strength parameters. There are two stages of loading in any typical shear strength test. First is application of a confining stress, and the second stage is application of the shearing force. There are two major types of tests which are commonly used in the laboratory: the direct shear test and the triaxial shear strength test. In the direct shear test, the first stage of the so called confinement corresponds to the application of the normal load. If I have a direct shear sample, this is the failure plane. Application of the normal load sigma n corresponds to the confining stress, and the application of the shear stress until failure corresponds to the second stage of loading. On the other hand, if I have a triaxial test specimen, then application of the lateral confining pressure sigma 3 corresponds to the first stage of loading, and as you know, sigma 3 will get applied equally at the top and bottom as well, because the specimen is kept in a perspex container carrying water, and then subsequently increasing sigma 3 to its final value sigma 1, that corresponds to the application of the second stage of loading, that is the deviatoric stress sigma 1 minus sigma 3, half of which corresponds to the maximum shear stress. This diagram shows the various stages in loading. The first stage of loading corresponds to application of sigma 3. While applying sigma 3, we could either allow drainage and allow consolidation under this pressure sigma 3, or not allow drainage and not permit consolidation. And in the second stage of loading, when we apply the deviatoric stress, either we could allow volume change, in which case drainage is permitted, that is the implication, or we may prevent volume change, which means no drainage is allowed. So, the first stage has two possibilities, the second stage has also two possibilities, and combining the two we have therefore 4 different combinations, out of which one is not a realistic combination, and therefore we normally use 3 combinations of the first and second stage loadings. Accordingly, we have 3 types of tests. First one is consolidated drain test, second is consolidated undrained test, the last one is unconsolidated undrained test. We do not use the unconsolidated drained test, that combination, because it is not a realistic one. It does not normally happen in the field. The names which are normally used for these tests are CD, CU and UU. Now, let us see the mechanics of these tests, and unless we understand the mechanism involved in this test, how the stresses are changing, we will never be able to understand what is the kind of shear strength parameters which we are getting from these tests. Are we getting total stress parameters? Are we getting effective strength parameters? If we are getting the total strength parameters, how to get the effective strength parameters from them, and so on. Let us take the consolidated drain test first. The mechanics of the consolidated drain test is very simple. In the first stage of loading, that is application of confinement, drainage is permitted, and then the second stage, when shear stress is applied, volume change is permitted, that means in effect drainage is allowed. That is why this permits total consolidation to take place during the first stage of loading and drainage to take place during the second stage of loading, and that is why it is called consolidated drain test. This implies that the loading is slow enough to allow water to expel and not build any pore pressure. With the help of the diagrams which we had seen a little while earlier, we can say that in the first stage drainage is allowed and consolidation is permitted, and in the second stage volume change is allowed and drainage is permitted. We now come to the most important aspect of this test, that is the way the stresses change during the test. Let us take a look at this table. There are 4 items here: the type of loading that is applied, the total stress, the stress in the water, neutral stress, and the effective stress that is transmitted to the soil grains. The first stage of loading is application of the confining pressure. Let us call this delta sigma 3. When a pressure delta sigma 3 is applied horizontally, or since we are applying a fixed value of confining pressure, we may as well call it as sigma 3 and not as an incremental stress delta sigma 3. Then whatever stress we apply immediately becomes a total stress taken by water, and the total stress values will therefore be lateral pressure sigma 3 equal to the applied pressure sigma 3. The vertical pressure is also equal to the applied pressure sigma 3 because the sample is surrounded by water on all sides. Corresponding pressure in water will depend upon whether drainage is permitted or not. Now, this is a consolidated drain test, and therefore drainage permitted and consolidation is permitted, which means that the water does not take any stress. Neutral stress is 0, u equal to 0 both in the horizontal lateral direction as well as in the vertical direction, and whatever stress we apply therefore become effective stresses. Sigma 3 dash, the effective stress in the lateral direction, becomes equal to the applied stress sigma 3. So also the vertical pressure sigma 1 dash becomes equal to the applied stress sigma 3. Now comes the second part of loading, that is application of the incremental vertical stress. Let us say the vertical stress applied is delta sigma 1. Then the total stresses will obviously be the original total stress plus delta sigma 1. Since delta sigma 1 is applied only in the axial direction, sigma 1 becomes sigma 3 plus delta sigma 1, whereas sigma 3 remains as sigma 3. Once again, during the application of this axial load, during shear, we permit drainage, we permit volume change, we do not restrict it. Therefore, U is again 0, there is no pore pressure developed, which means that the effective stress is applied pressure once again. Sigma 1 dash is sigma 3 plus delta sigma 1, sigma 3 dash is equal to sigma 3. That means all the stress that we applied during this test get converted into effective stresses. Let us see next. Therefore, the typical Moore diagram for this will involve sigma tau plot with a Moore circle and a corresponding envelope, which will give us an effective value of cohesion and an effective value of friction angle, and these are usually called as C and phi d corresponding to the drained condition. Now here it is very important to remember that in nature soil undergoes consolidation over ages and millions of years. There is always a possibility that the soil which we test has already undergone some pre-consolidation. So if we have an over consolidated soil, then the confining pressure we apply may not necessarily be the pressure corresponding to that pressure which has already experienced in the past. If the pressure we apply is less than the pressure to which it has been subjected earlier, then the soil will behave like an over consolidated soil. On the other hand, it will behave like a normally consolidated soil. So if it is a normally consolidated soil, we will get a straight line envelope. If on the other hand it is an over consolidated soil, it will show a higher strength as given by this green dotted line until the applied normal stress becomes equal to the pre-consolidation pressure, and beyond that, once again the Moore circle of the over consolidated soil follows the envelope of the normally consolidated soil. That means after the pre-consolidation pressure is exceeded, for that higher pressure the soil, even the so called over consolidated soil, is actually relatively a normally consolidated soil. So if the soil is normally consolidated, if sigma 3 is greater than Pc, where Pc is the pre-consolidation pressure, then envelope is linear and it will pass through origin. Now why should the drained test envelope pass through the origin? It should pass through the origin because the origin corresponds to a pressure of sigma 3 equal to 0. A soil with sigma 3 equal to 0, saturated soil, corresponds to a slurry, and a slurry does not have a shear strength, it is a liquid, and therefore at sigma 3 equal to 0 there will be no shear stress, no shear strength in a totally drained test. Therefore the envelope should pass through the origin. On the other hand, if the soil is over consolidated, it will not pass through the origin. That is what the next slide shows. The initial part of the envelope will be non-linear. A consolidated drain test is a very slow test. Shearing has to be done at such a slow rate that pore pressures are not allowed to build up, and what it gives are shear strength parameters C dash and phi dash. Now where do we use this C dash and phi dash? What is the application of this test? The application of this test lies in the fact that it gives us effective strength parameters, and they are very useful wherever this test condition replicates the field condition. In the field, if we have gradual loading and if volume change is permitted and drainage is allowed, and that is what happens, for example, in an embankment which has been in existence for several years, for a very long term. It has already gone undergone consolidation, and therefore, if it undergoes slow shear, it will exhibit effective strength parameters C dash and phi dash. C dash and phi dash can therefore be used for analyzing the effect of gradual loading or long term stability of an embankment. Now, let us take the next test, that is the consolidated undrained or R test. It is also called the R test. The difference between this and the previous test is, here consolidation is permitted in the first stage of loading, but in the second stage of loading drainage is not permitted, volume change is not allowed. Therefore, we get total stress parameters in this, because unless drainage is permitted, the stresses do not become effective. Like last time, if we take a look at this diagram, we find that in the first stage drainage is allowed, consolidation is permitted, whereas in the second stage it is undrained during the application of the deviatoric stress. This table is now important. Mechanics of the consolidated undrained test. Like the consolidated drain test, we have here a column for loading, then 3 columns for total, neutral and effective stresses. The loading, first stage is that of application of delta sigma 3, second stage is the application of delta sigma 1. Since we are actually applying a finite value of lateral pressure sigma 3, this so called applied increment in loading can be considered to be nothing but sigma 3. The total stresses will obviously be the applied stresses, and therefore sigma 1 equal to sigma 3, sigma 3 equal to sigma 3. And since consolidation is permitted, U is 0, effective stresses will be the applied stresses. This part of loading and the corresponding stresses are identical to the earlier test. When the axial load is now applied, then comes the difference. This total stresses remain the same because the axial load gets applied as total stress. Now the water is not free of stress because undrained conditions prevail. U in water is delta sigma 1, the applied axial load, both in the horizontal direction and in the vertical direction, because the specimen is surrounded by water in a perspex cylinder. But the effective stresses will be sigma 3 plus delta sigma 1 minus delta sigma 1, that is sigma 3, whereas sigma 3 dash will be sigma 3 minus delta sigma 1. Thus, the effective stresses are not equal to the applied stresses, but slightly less. And where do we use this test, this kind of a test? Before that, let us see what a Morse circle looks like for this. Since this is a consolidated undrained test, the pore pressure developed, the applied load delta sigma 1 will both be equal irrespective of what the value of sigma 3 is. So, if we were to draw a Morse circle, if point E corresponds to sigma 3 and point B corresponds to sigma 1, the diameter delta sigma 1 is the applied stress under drained conditions, and the total stresses will therefore be sigma 1 and sigma 3 as shown in this figure. And to get the effective stresses, we have to subtract the pore pressure, which is equal to delta sigma 1. If I subtract delta sigma 1, I get this dotted circle whose point on the left A corresponds to the effective stress sigma 3 minus delta sigma 1. The point E for the left circle has a value of sigma 3, which is nothing but the effective stress as far as this is concerned. The Morse envelope, if it is plotted for the total stresses, then that will give an intercept CCU, because this test is called consolidated undrained. The intercept is called CCU and the angle is called phi CU for the envelope. On the other hand, if we plot the effective stress Moore diagram, obviously as per the reasoning we gave a little earlier, the envelope should give you the drained friction angle and it should pass through the origin O, as long as this soil is a normally consolidated soil. In this test, the pore pressure buildup is allowed during the application of shearing. This can give C dash and phi dash because we know what will be the magnitude of the pore pressure. We do not have to really measure, though we do measure in a typical test for validation, but we know that the pore pressure is equal to the applied vertical stress, and therefore C dash and phi dash can be easily calculated, and Cu and phi Cu of course can be calculated from the total stress readings which are directly obtained from the test. Where do we apply this test? This test is good for situations where an embankment, for example, has spent a little bit of its life and now it is undergoing a sudden unloading. In such a case, Cu or phi Cu will apply. Examples are dewatering, sudden drawdown. Now, mechanics of unconsolidated undrained test, that third kind of test. Here drainage is not permitted either during the first stage of loading or through the second stage of loading. As per this diagram, therefore, both in the first stage and in the second stage drainage will not be allowed, and therefore the soil is neither consolidated nor is volume change permitted. The mechanics now will be slightly different. Let us take the loading column and the stress columns. Under the loading column, although we are applying a confining pressure and an axial load, in this case, as you will be seeing during the course of the discussion, we need to add another loading which is due to the initial overburden. The reason is not far to seek. Because this is an unconsolidated undrained test, the confining pressure that we apply to the sample does not get transmitted to the soil grains, and it remains as a total pressure, and therefore when you shear this sample, soil should show no strength at all. But on the other hand, the soil does show some strength, because even before applying the confining pressure delta sigma 3, the soil already has some pressure due to the overburden. So we must begin with the overburden loading in order to see the effect of the undrained confining pressure and undrained axial load applied. The overburden pressure will be an effective pressure because sufficient time has passed in history during the formation of the soil, and sigma 1 and sigma 3 will both be equal to the overburden pressure sigma 0 dash, which can be taken as the effective stress. Pore pressure will of course be 0 under the normal natural conditions, and the effective stresses will also be equal to sigma 1 dash and sigma 3 dash, both equal to sigma 0 dash. Now when you apply the confining pressure, the pressure that we apply additionally gets added to the total stresses, and so we have sigma 1 equal to sigma 0 dash plus delta sigma 3, and so is sigma 3. And because undrained conditions prevail, pore pressure is not 0 now, it is equal to the applied pressure, incremental pressure delta sigma 3, delta sigma 3. The effective stresses will be sigma 1 dash equal to sigma 0 dash and sigma 3 dash equal to sigma 0 dash, meaning no effective stress is produced during the application of the confining pressure. Similar situation profiles when you apply the axial load. Total pressure gets increased by delta sigma 1 in the vertical direction. Pore pressure gets increased by delta sigma 1 both in the vertical and also the horizontal, and the effective stress gets modified into sigma 0 dash minus delta sigma 1 in the horizontal direction. The Morse circle for this will involve similar Morse circles. Suppose I consider two Morse circles with two different confining pressures, sigma 0 dash plus sigma delta sigma 3a or sigma 0 dash plus delta sigma 3b. Since undrained conditions prevail, they will both have the same value of deviatoric stress equal to delta sigma 1, and the Mohr envelope will be a common tangent which will be horizontal, because due to the total undrained conditions that are prevailing, friction will not get mobilized in this particular test. Phi u will be equal to 0. Here is another example of the same. If I conduct three different tests with different values of sigma 3, sigma 3a, sigma 3b, sigma 3c, and correspondingly also calculate the major principal stresses and plot Moore diagram, the common tangent will give me an undrained cohesion Cu and a friction angle phi u equal to 0. But if I have measurements of the pore pressure value here, then I can subtract the pore pressure values from these applied stresses and get the effective stress values, which, as I have shown in the previous table, will be sigma 3 dash equal to sigma 0 dash minus delta sigma 1 and sigma 1 dash equal to sigma 0 dash, and this being effective stress, it will give an envelope which will give me an effective friction angle and 0 cohesion, because that will correspond to fully drained conditions. This is what the set of Moore circles will look, and this is the final position as far as the effective stress conditions are concerned. Now let us see a few aspects corresponding to these tests. As delta sigma 3 increases, since no drainage is permitted, the pore pressure increases by the same amount and the effective stress remains unchanged. The change in pore pressure during shearing is a function of the initial effective stress and the moisture content. As these are identical for all the samples, the strength obtained is also identical. Now if we are having a sample which is not fully saturated, then phi u equal to 0 will not apply and Cu will not be constant. Undrained analysis cannot be conducted. In an undrained test, totally undrained test, it is a quick test, so both confinement and pore pressure and shearing was done rapidly and no pore pressure is allowed to build up, and the values of Cu and phi u which we get out of these can be used where similar conditions exist in the field, that is conditions of rapid construction, and therefore it is good for short term stability of an embankment or the stability of an embankment during the construction process itself, when the construction is rapid enough not to allow pore pressures to dissipate. Finally, we can make a statement that C is equal to 0 and C dash is equal to 0 for a normally consolidated soil in a fully undrained test, and for granular soils also C equal to 0 and C dash is equal to 0, but in an unconsolidated undrained test phi u equal to 0. We will see the practical significance of this in the next lecture. It is important to understand the practical significance of these tests, and for that purpose we will take into account a typical earth dam and various stages like the construction stage, the drawdown stage and the long term stage of its life. Thank you.